Alright, so this next lecture is on Chapter 10, which deals with fluids, in this case being fluids being in terms of a liquid, also in terms of a gas. And so the first thing then is in terms of density. And so density is given to be the amount of mass per unit volume. And so here density, the units of mass will be in terms of kilograms. The units on volume will be in terms of cubic meters. So density will be in terms of kilograms per cubic meter. So for example, you get something like this. What will be the density? Of an object that has a mass of 5 kilograms and occupies a volume of 2 cubic meters. So in density will just be the mass divided by the volume, and so my density here in this case will be the 5 kilograms divided by the 2 cubic meters, and we end up at 2.5 kilograms per cubic meter. So we get in terms of the density of my object. Well, the other thing that goes with density then is a term called specific gravity. And specific gravity then is basically in terms of how this compares to water. So it is the ratio of the density of the object so density of the object or the substance compared to the density of water. And it's actually water at a particular temperature, and that is at 4 degrees Celsius. And water at that temperature is 1 times 10 to the third cube. So it's a ratio. So I have density and then specific gravity. Well, when it comes in terms of a gas, we want to look in terms of pressure. Okay? And so pressure then, let's change the background, is going to be in terms of the amount of force per unit area. So pressure is the amount of force per unit area. So we need this when we talk about it in terms of gas. We could also look at it in terms of how much pressure do you put on your feet when you are standing. So for example, in terms of something like that, you got how much pressure is exerted by a person with a mass of 100 kilograms, given that the feet cover an area of 500 square centimeters. Well, again, for this, pressure is going to be in terms of force per unit area, which again, force will be in terms of newtons. Area is going to be in terms of square meters. Okay? And so here, the force acting on your feet is going to be due to the weight of the person. And so the pressure is going to be given by mg over A. We know the mass. The mass was 100. G is 9.8. But then this is 500 square centimeters. That needs to be converted into square meters. And again, from the handout you have, there is conversion factors for converting. And so this will become 0.05 square meters. And so we end up that the pressure is going to be 19,600 newtons per square meter. So that's how much pressure acting on the person's feet. Okay. Well, pressure in terms of a fluid, however, so in terms of something like this, so pressure for a fluid is that pressure will be given by the density times G times H. And so that's square P here. This is the density, which will be in kilograms per meter cubed. G is gravity, which will be 9.8. And then H is the height of the column, which will be in terms of meters. And so we can find how much pressure is acting. And so in terms of this scenario, we got basically a water tower and a pipe. We want to know how much pressure is being delivered to this pipe down here that feeds into the house. And so the pressure here will be given by rho G delta H. And for water, this number is going to be 1,000, had it up earlier. And so my pressure will be 1,000 times 9.8 times 30. And so the amount that's being delivered to my pipe is going to be in terms of this pressure. 2.9 times 10 to the 5th newtons per meter squared. So we have in terms of our liquid here, in this case water, to a pipe. We can also look in terms, again, in terms of a gas, and we get in terms of atmospheric pressure. And then also gauge pressure. And so you have that 1 atm, so you think in terms of here in Seattle, we're basically at sea level, is going to be given by 1.013 times 10 to the 5th newtons per meter squared, which is also 101.3 kilopascals. And so I end up the proper units here in terms of physics for talking about pressure of gas will be in terms of pascals. So in terms, we get that the total pressure is going to be given by the atmospheric pressure plus the gauge pressure. So this is the atmospheric, and then this is the gauge pressure. So we can look in terms of finding the total pressure. So if we know the pressure on a gauge, so like in terms of your tires, you know that pressure, you know the pressure outside, you get the total pressure being felt. Now, we got to look in terms of this and what is called Pascal's principle. And so you think in terms of if you go to your local auto mechanic and they put your car up on a lift, is basically they flip a switch and then the piston rises and brings your car up in the air and they can work on it. And so the way this works is in terms that the force in over the cross-sectional area is equal to the force you get out over the area. Oh. And so you got that if we look at F out over F in, we get in terms of what's called the mechanical advantage. Okay? So we can get how much basically work we can do. Right? So F out over F in is the mechanical advantage. So in this particular case, you got it, the area of the output is 20 times that of the input. You got that mechanical advantage is going to be 20. And so we got that how much force we can get out is we got that F out, that we're going to get that 20 times our 200, and we can lift a car that's 4,000 pounds. And so we got that we can get this car up into the air by using this. So in terms of another example of how this would work, so let's say that the force applied in is given to be 30 newtons. The cross-sectional area in is given to be 0.2 meters squared. The area out is given to be 1 meter, and I want to know how much force we generate out. So we get 30 over 0.2 is going to equal about over 1. And so again, the way we solve the proportion is to cross multiply divide. And so it ends up that the force we get out is going to be 30 times 1 divided by 0.2, and we end up with a force of 150 newtons out. So we have in terms of Pascal's principle. Also in terms of objects, we can look in terms of how they act when you put them in water. And so you get to Archimedes. And you get the story of Archimedes, who was given the task of figuring out whether or not the crown that was given to the king was made of gold or not. And the story is, the way that he figured that out is he noticed when he got into a bathtub that the water level rose, and so when screaming through the town naked, Eureka, that he had an idea as to how he could find out about his crown. And so you get in terms of what is called the buoyant force. So the buoyant force is given by the mass of the water displaced times gravity, which can then be given by the density of water times the volume displaced times G. And so we get that script P is density, V is the volume of the object, which will be equal to the volume of the water displaced. So this is the volume of the object. And again, G is gravity, which will be 9.8 meters per second. Okay. And so we can use this problem, in order to figure out in terms of, is the crown made of gold or not? And so we have in terms of this. Right? So is this crown made of gold or not? So we got that in air, the crown has a mass of 14.7 kilograms. And then when it's suspended in a tank of water, it has a mass of 13.4 kilograms. And we want to know, is it made of gold or not? Right? So we can look in terms of the water, and so we get that W prime, and this is going to be the weight in water, is going to be the tension, which will be W minus the buoyant force. Right? And so if I take this and we solve this, we get that W minus the weight in water is going to be equal to the buoyant force. Right? We also have, in terms of this, that W here is given by mass times gravity, which will be equal to the density times the volume times G. We also have that W minus W prime, which is equal to the buoyant force, is also given by the density of the fluid times the times G. And so we have in terms of that. And so we can look in terms of the ratio of these two quantities. And so the weight over the difference of the weights between water and air is going to be given by the density, L6 times V times G, over the density of the fluid, E times G. Well, the volumes here are the same, and so V here will go away. And so we get this ratio is going to be equal to density of the object over the density of the fluid. And so in terms of this two, V and G are both the same number top and bottom, so they go away. And so we can look here in terms of this. And so here, my density of my fluid is that we did this in water, which, so this is 1,000 kilograms per cubic meter. And so basically we're looking at here in terms of what is the specific gravity of my object. And so we have 14.7 over 14.7 minus 13.4 is going to equal, in this case, we get 11.3. And by comparing this number to the chart in the book, which did not copy well to be able to place in here, we find out that 11.3, that this corresponds to the density of lead, and therefore the crown is not gold. So my crown is not made out of gold, and the king got chipped. Okay. So we look at that in terms of an object in water, and actually this whole scenario will be similar to one of the labs we will do in class. Okay. But you also look in terms of buoyant force, we think in terms of a balloon. So here we have a helium balloon, and we want to know how much helium has to go in this balloon in order that it will be able to go up in the air. Okay. So again, the buoyant force is going to be given by the mass of the helium plus the mass of the load, which is 180, times G. Well, by using Archimedes' principle, we get that the density of the air times V times G is going to equal the density of helium times the volume of the balloon plus 180 times G. Well, G is common to both terms, and so G can be canceled out, and so the density of the air times V is going to equal the density of helium plus 180 times V. Okay. Again, we want to solve this for V, so I need to get my V terms on the same side. So let's take this over to where the air is. So we subtract this one out. So we end up with the density of the air times V minus the density of helium times V is going to equal 180. Now we can factor the V out, and so the volume is going to be the density of air minus the density of helium, 180. Next step is to divide, so we divide both sides by densities. And so the volume of the balloon will be 180 over the density of air minus the density of helium. And so again, from your book, from the chart, you get that the density of air is given to be 1.29 kilograms per cubic meter. The density of helium is given to be 0.179 kilograms per cubic meter. And so we can take those numbers and we can plug those in. And we end up that my balloon has to occupy a volume of 160 cubic meters. So we have in terms of that. Now, we can also look what happens to a fluid basically as it flows through a pipe. And so you get in terms of what's called the continuity equation. And so now we're looking what happens when you have something like this. And so we have, this is going to be V1. This will be cross-sectional area A1. And then we look what happens as it comes out this end. So we get in terms of V2, and then what would be cross-sectional area A2. Some of you have seen this before. If you think in terms of a garden hose, you turn it on, you have no nozzle at the end, and the water just sort of flows out. And then you put your thumb over the end and make the opening smaller, and it comes out at a greater velocity. And so in terms of this equation then, we get that the density times A1, B1 is going to be the density as it comes out the opening times the area and its velocity. Okay. Well, if the fluid is not compressible, so if the fluid cannot be compressed, so if the fluid is incompressible, then the density will not change as we go from one end to the other. And this will be true in terms of, for most liquids, so true for liquids and for some gases. So we have it in terms of that. So in that simple case, we get that A1 times V1 will equal A2 times V2. Okay. So an example of a problem for that would be given something like this. So what will be the velocity of water the initial velocity is 4 meters per second, and the cross-sectional area is 1 meter squared, and the opening at the other end is now 0.2 meters squared. Okay. So we got A1 V1 equals A2 V2, and so we get 4 meters per second squared times 1 is going to be equal to 0.2 times V2. So this is simple enough. All we have to do here to solve this is we just need to divide both sides by 0.2. So we divide this by 0.2, we divide that by 0.2, and so we end up that my new velocity here, when it comes out, it will be going out at a rate of 20 meters per second. So we have in terms of this. So if you look in terms of this equation and my drawing, we got that that's also basically the drawing of a jet engine, and so Boeing Corporation looks at air as a fluid. And so you can look at it in terms of this. And with that, that will conclude Chapter 10.